nationally accepted basic reference standard against which the measurements of any physical quantity are compared. In physics, we deal with many physical quantities and their units. However, very few basic units are required to express these physical quantities. Most physical quantities are expressed in terms of some base quantities. These base quantities are referred to as fundamental quantities. For example, distance, which is a measure of length, is a fundamental quantity. It's the same with time. The other quantities, which are expressed in terms of their fundamental quantities, are called derived quantities. For example, area or volume, which is expressed in terms of multiples of length, is a derived quantity. Similarly, speed is a derived quantity as its measurement depends on distance and time. The units of fundamental or base quantities are called base units or fundamental units. The units of derived quantities are expressed as a combination of base units. Such units are called derived units. Base units and derived units together make up a system of units. A system of units is a generally accepted set of units of measurement. Until recently, three major systems of units were in use in different countries based on the units of three fundamental quantities, namely length, mass, and time. Among these were the CGS system, which stands for centimeter, gram, second, and FPS, which stands for foot, pound, second, respectively. These units are adopted by Britain, and hence the system is referred to as a British system. The third system of units is the MKS system, which stands for meter, kilogram, and second. However, in 1971, the General Conference on Weights and Measures recommended a standard set of units of measurement with their symbols and abbreviations. This system is known as Système International des Units, French for International System of Units, abbreviated as SI. Currently, SI units are followed globally for all scientific, academic, commercial, technical and industrial purposes. In SI, there are 7 base units for the 7 physical quantities taken as fundamental quantities. Following are the quantities and their corresponding units. Length is measured in meters, denoted by the small letter m. Meter is the length of the path travelled by light in a vacuum during a time interval of approximately 300 millionth of a second. Mass is measured in kilograms, denoted by the small letters kg. Kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at International Bureau of Weights and Measures at Sèvres, near Paris in France. Time is measured in seconds, denoted by the small letter s. A second is the duration of approximately 9 billion periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Electric current is measured in ampere, denoted by the capital letter A. An ampere is that constant current which, if maintained in two straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in a vacuum, would produce between these conductors a force equal to 2 multiplied by 10 raised to the power -7 Newton per meter length of the conductor. Thermodynamic temperature is measured in Kelvin, denoted by the capital letter K. A Kelvin is a fraction 1/273.16 of the thermodynamic temperature of the triple point of water. Luminous intensity is measured in candela, denoted by the small letters CD. A candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 power 12 Hz, and that has a radiant intensity in that direction of 1/683 watt per steradian. An amount of substance which contains as many basic entities, such as atoms or molecules, in a system as equivalent to the number of atoms in a carbon-12 isotope is measured in mole, denoted by the small letters MOL. Apart from these base units, SI has defined two more units for two supplementary quantities, namely plane angle and solid angle. Plane angle d theta is the ratio of length of an arc of a circle to the radius of the circle, and is measured in radian, denoted by the small letters RAD. It is defined as the angle subtended at the center of a circle by an arc of length equal to the radius of the circle. Solid angle is defined as the ratio of the intercepted area dA of the spherical surface, described about the apex O as the center, to the square of its radius r, and is measured in steradian, with the symbol SR. If the magnitude of the intercepted area is equal to the square of the radius, then the solid angle is equal to 1 steradian. SI also retained some units from earlier systems for general use. They are minute, hour, day, year, degree, liter, ton, carat, bar, curie, roentgen, quintil, barn, hour, hectare, and standard atmospheric pressure. For all derived quantities, their units are derived from these base SI units. As SI units use the decimal system, it is easy to convert or derive units from base units in this system. You can easily measure length of various entities using appropriate instruments such as a tailor's tape for length of a cloth, a land tape for length of a building, a survey chain for length of roads, etc. However, lengths to be measured can be as large as distance between two heavenly bodies or as small as the radius of an atom. To measure large distances, we employ an important method called the parallax method. What happens if you look at an object with one eye closed? Its position seems to be moved a little from the original position. If you look at a pencil held in front of your eyes against a fixed reference point on a plain wall, with your left eye closing your right eye, and then with your right eye closing your left eye, you observe that the position of the pencil seems to change with respect to the fixed reference point on the wall. This is called parallax. You may call the two eyes are two different viewpoints, since when used separately, they create different lines of sight. Distance between these two viewpoints or points of observation is called basis. Here, the basis is equal to the distance between two eyes. We use exactly the same method to measure the distance of a distant planet. Instead of two eyes, we view the planet from two different observatories on the Earth at the same time. Let X and Y be two observatories viewing the planet S from two locations on the Earth. Thus, XS and YS are the lines of sight of the planet from the two observatories respectively. Here, the distance B between X and Y is the basis which is known. Thus, XYS forms a triangle. Let beta and gamma be the angles made by the lines XS and YS with the line XY respectively, and angle XSY be theta. The angles beta and gamma are measured while observing the planet with the help of telescopes. As the sum of the angles in a triangle is equal to 180 degrees, and knowing the values of beta and gamma, we calculate the angle XSY between the two directions along which the planet is viewed from these 2 points. This angle, denoted by theta, is known as parallax angle or parallactic angle. As the planet is at very large distance from the Earth, say D, its distance from the two observation points on the Earth, namely XS and YS, can be approximated to be equal. As D is large, the ratio of B to D is less than 1. This implies that the parallax angle theta is very small. Subsequently, we consider X and Y as 2 points on arc of a large circle with its center at S and radius D. By definition of angle, theta is equal to the ratio of the arc length, which is the basis B to the radius of the circle D, where theta is taken in radians. Thus, basis B is equal to d theta. This implies that the distance of the planet D from the Earth is the ratio of B to theta. As we measure the distance of a faraway planet from the Earth, we can also measure the size or angular diameter d of the planet. If d is the diameter of the planet, and alpha is the angle subtended by the planet's diameter at the Earth, we have alpha equal to d by d, or d is equal to d alpha, where alpha is in radians. The angle alpha can be measured from a single location on the Earth. It is the angle between the two directions when two diametrically opposite points of the planet are viewed through the telescope from the observation location. For the purpose of these measurements, you must know the conversion of degrees into radians. 1 degree or 60 minutes is equal to 1.75 into 10 power minus 2 radians. 1 minute or 60 seconds is equal to 2.91 into 10 power minus 4 radians. 1 second is equal to 4.85 into 10 power minus 6 radians. That was about large distances. Let us now look at the other side of the coin. That is, smaller distances. To measure very small distances, such as the size of a molecule, we cannot employ devices like a vernier calipers or a screw gauge. Special microscopes need to be used. However, all such instruments have certain limitations in measuring lengths. We can use a simpler method to estimate the size of a molecule. Let us take some oleic acid. We can use a simpler method to estimate the size of a molecule. Let us take some oleic acid. Oleic acid is a soapy liquid with large molecular size of the order of 10 power minus 9 meter. To start with, we prepare a 20 cc of alcohol oleic acid solution with 1 cc of oleic acid in it and dissolve 1 cc of this solution in alcohol to dilute it to 20 cc. This makes the concentration of oleic acid as 400th part of the solution. Next, we take water in a large trough and sprinkle some lycopodium powder on its surface. Lycopodium powder is a yellow tan powder that spreads uniformly throughout the surface of water, forming a thin layer. Then, put 1 drop of alcohol oleic acid solution in this trough. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. By pushing away the lycopodium powder from the point where the drop is dropped on the surface. This makes the circular film of the acid drop identifiable on the water surface. Quickly, we measure the diameter of this circular film to determine its area, A. Let the approximate volume of a drop of solution dropped on the surface of water in the trough be V centimeter cube. As the concentration of oleic acid is 1/400 in the solution, the volume of oleic acid in each drop of the solution is V/400 centimeter cube. Since only 1 drop of solution is put in the water, the volume of oleic acid on the thin film is equal to the volume of the drop, that is, V/400 centimeter cube. Now that we have the area and volume of the thin circular film, we can get its thickness, T, as the ratio of volume to area. T is equal to V/400 a centimeter. If we assume that the film is monomolecular, as the concentration is very low, the thickness of film becomes the size of a molecule of oleic acid. We learnt how to measure a tiny molecular distance or a massive stellar distance. There are various scales of measurement in this range. A brief chart of the measurable distances is shown here. Some of these units are named for usability purpose, such as Fermi, denoted by small letter f, which is equal to 10 to the power minus 15 meter. Angstrom, denoted by accented A, equal to 10 to power minus 10 meter. Astronomical unit, denoted by AU, that measures average distance of the Sun from the Earth, which is equal to 1.496 into 10 to the power 11 meter. Light year, denoted by small letter ly, which is equal to 9.46 into 10 to the power 15 meter. A light year is the distance that light travels with velocity of 3 into 10 to the power 8 meter per second in 1 year. Parsec, denoted by small letters PC, which is equal to 3.08 into 10 to the power 16 meter. Mass is the basic property of matter and a fundamental unit of measurement, since its measurement does not depend on any other physical quantity. The SI unit of mass is kilogram, denoted by small letters kg. We observe the standard kilogram weight used by different shopkeepers. But the prototype of the standard kilogram is supplied by the International Bureau of Weights and Measures, BIPM. The copies of the standard weight are available worldwide, including National Physical Laboratory in India for standardization of mass locally. If the magnitude of the mass of the object to be measured is much higher than the kilogram, say, for example, the mass of a paddy bag, unit like quintal, which is equivalent to 100 kilograms, is considered. Another higher unit is the ton, which is equivalent to 1000 kilograms. Masses of cargo containers are expressed in tons. Different types of balances are used to measure masses of objects of varying magnitudes. They range from electronic balances used in gold shops, common balances used in grocery shops, and platform balances used to weigh heavy articles such as reams of construction rods. However, some objects are either so large or so small that their mass cannot be measured using balances. For example, the mass of heavenly bodies, like planets and stars, or the mass of subatomic particles, like an electron or a proton, cannot be measured by direct usage of a balance. We employ indirect methods and techniques by which we can measure their masses. For example, the mass of heavenly objects can be estimated using Newton's universal law of gravitation, which you will learn later in the course. Mass of subatomic particles, like electrons, can be found by making use of devices like mass spectrograph. In a mass spectrograph, a stream of charged particles, like electrons, in rectilinear motion is subjected to electric and magnetic fields. Due to the effect of the fields, the particles then follow a curved path. Then the radius of the curved path of the particles, which is dependent on the mass of the particle, is observed. From the radius of the path observed, the mass of the particle is estimated. The usage of the unit kilogram is not convenient for measuring the masses of the particles like atoms or molecules. Hence, for measuring the masses of the particles like atoms or molecules, a convenient unit called Unified Atomic Mass Unit, referred to as AMU in short, was established. The symbol of Unified Atomic Mass Unit is U. One Unified Atomic Mass Unit is defined as mass of 1/12 the mass of an isolated atom of carbon-12 isotope, at rest and in its ground state, including the mass of the electrons. It is equivalent to 1.66 into 10 power minus 27 kilograms. The masses of different objects we come across in the universe have a huge variation. The table that follows shows the range and the order of the masses of different objects. Measurement of time is of utmost importance for us in our day-to-day life, and even in the history of science. Measuring time gives the chronological order of events that take place and helps in better conceptual and factual understanding of science. Measuring time is measuring the time interval between two events. For example, in a marathon race, the time interval between the instant of start of the race and the instant the winner crossing the finish mark is essential to declare a winner in the race. The ordinary watches, the devices that we normally look at to know time, do not help in deciding the winner, as the events of two persons crossing the finish mark can vary in a fraction of seconds. To increase the accuracy, we require the time measuring devices that can measure the smallest fraction of a second, the standard SI unit in measuring time. There were so many kinds of time measuring devices used in the past, ranging from the hourglasses, pendulums, sundials, etc., which measure time based on different phenomena. To have the most accuracy in measuring time, now we use an atomic standard of time, which is based on the periodic vibrations produced in a cesium atom. Hence, the clock is also referred to as the cesium clock or the atomic clock. In its cesium clock, the second is taken as the time needed for 9,192,631,770 vibrations of the radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium-133 atom. The vibrations of the cesium atom regulate the time shown by this atomic clock, just as the vibrations of a balance wheel regulate the time shown by an ordinary wristwatch. The cesium atomic clock has an accuracy of 1 second in 1 million years, or an uncertainty of plus or minus 1 into 10 power minus 13. The number of seconds in a year is 3.1536 into 10 power 7. Hence, the atomic clocks lose or gain no more than 3 microseconds in 1 year. That is why a set cesium atomic clock is used at the National Physical Laboratory, NPL, New Delhi, to maintain the Indian standard of time. The time intervals of events that we come across in the universe vary over a very wide range. Some of the major time intervals are shown here in multiples of seconds. In measurements, accuracy and precision are two important terms. For example, if 5 darts are thrown and all hit the bullseye, each throw is said to be accurate and precise. Accuracy is the degree of closeness of the measured value to the true or actual value. How close the darts land to the center of the bull's eye determines the accuracy of the throw. Precision is the degree of resolution of a measured value when the same quantity is measured with different devices. If all 5 darts land at the same point, then the throws are said to be precise. Take, for example, an object whose absolute length is 32.56 mm is measured using 2 different instruments. Using the first instrument with a resolution of 1 mm, we obtain the measurement as 32 mm. Let us call this measurement M1. Using the second instrument, with a resolution of 0.1 mm, we obtain the measured value as 32.5 mm. Let us call this M2. Here, M2 is more accurate as it is closer to the object's true value than M1. Also, M2 is more precise as the resolution of the instrument used is greater than that of the first one. Any quantity that is measured should be accurate and precise, especially in science and technology. In reality, however, measured values carry uncertainty. This uncertainty is called an error. Errors are classified as systematic errors and random errors. A systematic error is a unidirectional error. That is, it is either positive or negative. A systematic error can occur due to an imperfect instrument, a faulty measurement technique, or incorrect process of measurement. Errors may occur due to the use of an imperfect instrument for measurement. Such errors are known as instrumental error. For example, if the needle of a simple balance is skewed or bent, it always shows a weight that is more or less than the actual weight of the object being weighed. Errors may occur due to an imperfection in an experimental technique or procedure adopted while measuring. For example, keeping a thermometer under the armpit will not measure the body's exact temperature as the mercury bulb is exposed to external factors such as air in the room, humidity, etc. Errors may also occur due to an incorrect technique or procedure being followed while measuring values. Such errors are called personal errors. Parallax is one such error. While measuring the length of a line using a foot scale, if you tilt your head, the length measured will be shorter or longer by a millimeter or 2. Systematic errors can be minimized or eliminated by using a perfect measuring instrument and by improving the technique or procedure of measurement. Random errors are akin to what they are called random. These errors vary in terms of sign and size. That is, they can be either negative or positive, and the quantum of error varies in absolute terms. These errors can arise out of unpredictable situations, such as a sudden change in environmental conditions, voltage fluctuations, or mechanical vibrations in the experimental setup, etc. Random errors can be minimized or eliminated by ensuring that measurements are taken under stable conditions and using properly set up instruments. Another type of error is least count error. This can be associated with both systematic and random errors. Least count is the smallest value of measurement that can be measured using an instrument. All values are considered precise up to the least count of a measuring instrument. For example, if you are using a meter scale, its least count is 1 millimeter. Hence, any measurement error will be in multiples of millimeters, not less. In academic laboratories, the general equipment used to measure length is a vernier calipers and a screw gauge. The least count error in a vernier calipers is 0.01 centimeter and for a screw gauge is 0.001 centimeter. Least count error can be minimized or eliminated by using high precision instruments or improving experimental techniques. Another way to reduce such errors is to repeat the measurements and take the arithmetic mean to bring the measured value closer to the actual one. If n measurements are taken, say A1, A2, A3, A4, so on till An, then the final value will be taken as the arithmetic mean of these n measurements. In the absence of a true value of measurement, this arithmetic mean is treated as the true value. The magnitude of difference between the true value and each measured value of a quantity is called the absolute error of that measurement. It is denoted by mod delta A. Since an arithmetic mean is considered the true value, delta A1 is equal to A1 minus A mean. Delta A2 is equal to A2 minus A mean, and so on till delta An is equal to An minus A mean. Individual error, delta A, may be positive or negative. However, absolute error, mod delta A, is always positive. Mean absolute error is the arithmetic mean of absolute errors of all measurements. If we take a single measurement instead of n number of measurements, then the value of the measurement lies in the range A mean plus or minus delta A mean. This implies that any measurement of a physical quantity A is likely to lie between the values A mean minus delta A mean and A mean plus delta A mean. Instead of absolute error, we often use relative error. Relative error is the ratio of mean absolute error to mean value of the measurements. Relative error is denoted by delta A. When relative error is taken in terms of percentage, it is called percentage error. When a quantity is derived from more than one measured value, the error in the derived quantity may be a combination of errors in the values from which it is derived. For example, the volume of a cuboid is the product of its length, breadth, and height. If there is an error in measurement in length, breadth, and height, then the error in volume will reflect the combined effect of all three errors due to mathematical operations. Some common combination errors are error of a sum or a difference, error of a product or a quotient, or error in case of a measured quantity raised to a power. When two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. If two physical quantities have their measured values A and B, and mod delta A and mod delta B are their absolute errors, find the error delta C in the sum C is equal to A plus B. We have by addition C plus or minus delta C is equal to A plus or minus delta A plus, B plus or minus delta B. The maximum possible error is C. Delta C is equal to delta A plus delta B. For the difference C is equal to A minus B, we have C plus or minus delta C is equal to A plus or minus delta A minus B plus or minus delta B, which is equal to A minus B plus or minus delta A plus or minus delta B, or delta C is equal to plus or minus delta A plus or minus delta B. The maximum value of the error delta C is again delta A plus delta B. When two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. Suppose a measurement Z is equal to A into B, and the measured values of A and B are A plus or minus delta A and B plus or minus delta B. Then Z plus or minus delta Z is equal to A plus or minus delta A multiplied by B plus or minus delta B, or Z plus or minus delta Z is equal to AB plus or minus B delta A plus or minus A delta B plus or minus delta A delta B. Dividing left-hand side by Z and right-hand side by AB, we get 1 plus or minus delta Z by Z is equal to 1 plus or minus delta A by A plus or minus delta B by B plus or minus delta A by A into delta B by B. Since delta A and delta B are small, we shall ignore their product. Hence, the maximum relative error delta Z by Z is equal to delta A by A plus delta B by B. This holds true for division as well. The relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. If z is equal to a square, then delta z by z is equal to delta A by A plus delta A by A is equal to 2 into delta A by A. Hence, the relative error in A square is twice the error in A. In general, if Z is equal to A to the power P into B to the power Q divided by C to the power R, then delta Z by Z is equal to P into delta A by A plus Q into delta B by B plus R into delta C by C. Whenever we measure the length or weight of an object, we note the measurement in the form of numbers. Here's a brick. Let's measure its length. Observe that the length is between 15.4 centimeters and 15.5 centimeters. Since we are not sure, we can say that the length is approximately 15.45 centimeters. In this measurement, 1 and 5 in the whole part and 4 in the decimal part are certain, while the 5 in the decimal part is uncertain. This 5 is uncertain because this is an approximate value. The values of many measurements in real life are decimal numbers. Digits in decimal numbers can be categorized as certain and uncertain. The number of digits in a measurement which are certain plus one additional digit which is uncertain are together known as significant figures. There are rules to determine the significant figures in a given number. The first rule says that in any measurement, all non-zero digits are significant. For example, we weighed a bar of steel that measures around 62.45 kilograms. Here, all the digits are non-zero numbers. In this number, all the 4 digits are significant figures. The second rule says that in any measurement, all the digits, including zeros, are significant for a decimal number greater than 1. Here, we have the length of a water hose, which measures 6.407 meters. This number is greater than 1. There are 4 significant figures in this number. The third rule says that in any measurement, if the decimal number lies between 0 and 1, the zeros to the right of the decimal point, but left to the first non-zero digit, are non-significant figures. Consider any number. Say 0.006452. Observe that there are 2 zeros between the decimal point and the first non-zero digit, that is, 6. These zeros are non-significant figures. Hence, the significant figures in this number are 6, 4, 5, and 2. Therefore, the number of significant figures is 4. The fourth rule states that if the measurement is a whole number, then the case becomes ambiguous if there are zeros to the left of an understood decimal point, but to the right of a non-zero digit. To remove this ambiguity, the number should be reported in scientific notation. That is, a into 10 raised to power b. For example, let's take a number 2507000. This is a whole number. According to rule number 1, there are 7 significant digits in this number. However, in this number, there is an understood decimal point, which is usually not written. The rightmost non-zero digit in the number is 7. There are 3 zeros between the 7 and the understood decimal point. We can report this in scientific notation as 2.507 into 10 raised to power 6. Now, the number of significant figures in this number is 4, since 2.507 is greater than 1. The fifth rule says that in any measurement, all the final zeros in a decimal number obtained by rounding off a decimal to a given number of decimal places are significant. For example, let's take the number 9.8982. There are 5 significant figures in this number. Let's round off the number to 2 decimal places. The resultant number 9.90 has the digit 0. But this number is greater than 1. Therefore, 0 is also a significant number. The number of significant figures in this number is 3. Using the rules we just studied, decimal numbers can be rounded off to the required significant figures. There are certain rules to round off the uncertain digits in a given number. The rule by convention says that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5, and is unchanged if the latter is less than 5. Here is an example. We will round off 8.917 to 3 significant figures. This number has non-zero digits and there are 4 significant figures. In the decimal place, we will round off 7, resulting in the number 8.92. Here is another example. Round off 7.9342 to 4 significant figures. This number has non-zero digits and there are 5 significant figures. In the decimal place, we will round off 2, resulting in the number 7.934 as the number to be dropped, which is 2 is less than 5. Now, consider 2 numbers 3.945 and 3.975. Let us round them off to 3 significant digits. In this case, the insignificant digit to be dropped is neither greater than nor less than, but is equal to 5 in both the given numbers. To do this, we have another convention, which states that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Thus, the answers are 3.94 and 3.98 for the rounded off numbers as shown. Here, the length can be written as 8.1 plus or minus 0.1 or 8.1 plus or minus 1.2%. And the breadth can be written as 5.1 plus or minus 0.1 or 5.1 plus or minus 2%. Hence, using the combination of errors rule, the area of the field calculated as the product of these two quantities would be 41.31 plus or minus 3.2% or 41.31 plus or minus 1.3 square meters. We can report this as 41 plus or minus 1 meter square. Here, 1 square meter is the error in the result. Thus, the result also has two significant digits, which is same as the original data. Rule number 2 says that the relative error of a value of a number specified to significant figures depends not only on n but also on the number itself. If there are two quantities, say 10.01 meters and 80.5 meters, both carrying an error of 0.1 meter, then the relative error in 10.01 meters is plus or minus 1%, while the same for 80.5 meters is 0.12%. Another important point to remember with significant figures is that intermediate results in a multi-step calculation should be taken to an additional significant figure in every measurement than the number of digits in the least precise measurement. Consider a number, say 6.55. The reciprocal of 6.55 taken to the same number of significant digits, that is 3, is 0.152. However, the reciprocal of 0.152 is 6.58, which does not match the original data we had. Now, if we consider the reciprocal of 6.55 to 4 significant digits, we get 0.1527. The reciprocal of 0.1527 taken to 3 significant digits is equal to 6.55, which is the original data again. We learnt earlier about different physical quantities, of which 7 are considered fundamental according to the SI system of measurements, while the others are derived physical quantities. The 7 fundamental quantities are length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These are also referred to as base quantities. All other physical quantities can be conveniently derived from these base quantities. Thus, we have relationships between fundamental quantities and derived quantities. Therefore, when a derived quantity is expressed in terms of base quantities, the resultant expression is the product of different powers of the base quantities. For example, consider the quantity force. Force is product of mass and acceleration. Mass is a base quantity. and acceleration is the derived quantity, which is the ratio of change in velocity to time. Velocity, which is also a derived quantity, is the ratio of displacement to time. Displacement, in basic terms, is length. Thus, velocity can be expressed as the ratio of length to time. Using the same logic, we can write acceleration as length by time divided by time. Thus, the expression for a quantity force can be simplified as shown. From the expression, it is clear that the exponents of mass, length, and time in the expression for force are 1, 1, and -2 respectively. These exponents of base quantities in the expression for force are called dimensions. Thus, the dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We say the dimensions of force are 1 in mass, 1 in length, and -2 in time. For convenience, we use symbols to represent base quantities as follows. For mass, we use m. Length is denoted by L and time by T. The other four base quantities are represented by symbols of their SI units, namely electric current by I, thermodynamic temperature by K, amount of substance by mole, and luminous intensity by CD. The physical quantity expressed in terms of its base quantities is enclosed in square brackets to show that it is an equation among the dimensions of the quantity and not among the magnitudes. Thus we can write the expression for force as force is equal to mLT power -2 as shown. Such an expression for a physical quantity in terms of its base quantities is called its dimensional formula. An equation which equates the quantity with its dimensional formula is called a dimensional equation. Of the 7 base quantities in the SI system, we see that only 3, namely mass, length, and time, exist in the dimensional formula for force. Thus, we can say that the dimensions of all the other 4 base quantities in the expression for force are equal to 0. In mechanics, most derived quantities are related to only the 3 base quantities of the 7, namely mass, length, and time. Let us look at another example. Let us find the dimensional formula for pressure, which is equal to force per unit area. Area is the product of length and breadth. Length and breadth represent the base quantity, length. Thus, area can be expressed as length square. and hence its dimensional formula is L power 2. We know that the dimensional formula of force is mLT power minus 2. Now, the dimensional formula of pressure is obtained as shown. Following the same methodology, we find the dimensional formula for the volume of a body. Volume is the product of length, breadth and height. Height also represents the base quantity length. Thus, the dimensional formula of volume is L power 3. Similarly, we can find the dimensional formula of mass density, which is the ratio of mass to volume. The dimensional formula for density is ml power minus 3. So far, we have discussed derived physical quantities, namely force, pressure, and density. These quantities have units, namely Newton, Pascal, and kilogram per meter cube, respectively. But there are certain derived physical quantities that do not have units. For example, relative density is the ratio of the density of a substance to the density of water. As it is the ratio of two identical quantities, it does not have any unit. Therefore, the quantity relative density does not have any dimensional formula. Another example is absolute refractive index, mu, of an optical medium, which is the ratio of the speed of light in air or a vacuum to the velocity of light in the given medium. Refractive index is just a number and is significant even though it does not have any unit, because the value of mu of a medium indicates the extent to which a ray of light bends on entering the medium at a given angle of incidence. Refractive index of a given medium is constant and does not have any dimensional formula. You will learn about refractive index in detail later in the course. We also have certain physical constants, each of which has a unit as well as dimensional formula. For example, the universal gravitational constant G is a constant whose value is 6.67 into 10 power minus 11 Newton meter square per kg square and is denoted by the expression G is equal to force F into distance d square by mass m square. Thus, the dimensional formula of G is obtained as shown. We obtain the dimensional formula of G as m power minus 1 L power 3 T power minus 2. You will learn about G in detail later in the course. So far, we have discussed physical quantities, which are expressed as the product of base or other derived quantities. We also learnt that a dimensional equation is the equation among the dimensions of the quantity and not among the magnitudes. But we may encounter situations where we need to add or subtract different terms involving base quantities. It is very important to know that when we write L plus L, as shown, we mean length added to length. So, we get length. Again, it is not 2 times L as we are not adding the magnitudes of the length. Similarly, if velocity is subtracted from velocity, we get velocity. Thus, Lt power minus 1 minus Lt power minus 1 equals Lt power minus 1. The table shows the list of some of the physical quantities and their dimensional formulae. You will learn about the applications of dimensional formula later in the course. We learnt earlier about the dimensions of some physical quantities. The dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. An expression for a physical quantity in terms of its base quantities is called the dimensional formula. An equation which equates the quantity with its dimensional formula is called the dimensional equation. We will now learn about the uses of these dimensional formulae and dimensional equations. We know that a dimensional equation is the equation among the dimensions of a quantity and not among the magnitudes. Thus, when we write L plus L, as shown, we mean length added to length. So we get length again. It is not 2 times L as we are not adding the magnitudes of the length. This property of a dimensional equation can be used to check the dimensional consistency of equations by analyzing the dimensional formula of quantities on both sides of the equation. For example, consider the motion of a body moving with an initial velocity u and uniform acceleration a, having made a displacement s in a time interval t. The motion of the body can be represented by the equation s is equal to ut plus half at square. Let us now verify the consistency of this equation using dimensional analysis. On the left-hand side of the equation, we have displacement s. This is basically length and its dimensional formula is L. On the right-hand side of the equation, we have 2 terms, each involving the product of 2 different quantities. The first is ut and the second is half at square. When the magnitudes of 2 or more physical quantities are multiplied, their dimensions are also treated in the same manner as done with ordinary algebraic symbols. In this case, in the first term, it is the product of velocity and time. The product of the dimensions of these quantities is Lt power minus 1 into t, as shown. On simplification, we get L. The second term on the right-hand side of the equation is half at square. Half is a constant and thus does not have any dimensions. In the first term, it is the product of acceleration and time square. The dimensions of A are Lt power minus 2 and that of T are T. Thus, the dimensions of at square are as shown. Taking the dimensional formula of the physical quantities in both the terms on the right-hand side of the equation, substituting their corresponding dimensions and simplifying, we find it is equal to L, which is the dimension of length as obtained on the left-hand side of the equation. Thus, the dimensions of the quantities on both sides of a given equation are the same. This proves that the equation is correct. It is very important to note that physical quantities represented by symbols on both sides of a mathematical equation must have the same dimensions. This principle is called the principle of homogeneity of dimensions and is useful in checking the accuracy of an equation. This principle can also be used to derive expressions for physical quantities if the other quantities on which it depends are mentioned. For example, we can derive an expression for the time period of a simple pendulum, assuming that its time period t depends on the length, mass of the pendulum, and the acceleration due to gravity at a given place. Let us take the constant of proportionality k as 2 pi. We assume that the time period is proportional to L power A, M power B and G power C, where A, B and C are constants. Replacing the proportionality symbol, we get a constant k. Hence, the time period is equal to k into L power A, M power B, G power C. We now need to find the values of A and B using dimensions of the physical quantities on both sides of the equation. The dimensional formula for time is T. The dimensional formula for length is L. The dimensional formula for mass is M. The dimensional formula for acceleration due to gravity is Lt power minus 2. The constant does not have any dimensions. Hence, the dimensional formula of the quantities on the right side of the equation is simplified as shown. Let this be equation 1. The dimensional formula of the quantity on the left side of the equation is as shown. As we do not have the term for M and L on the left-hand side of the equation, we take their powers to be 0 as shown. Let this be equation 2. Equating equations 1 and 2. We compare the powers of the base quantities on both sides of the equation. Thus, we get B equal to 0, A plus C equal to 0 and minus 2C equal to 1. On simplification, we get the values of B equal to 0, C equal to minus half and A equal to plus half. Thus, the expression for the time period of the simple pendulum becomes 2 pi into the square root of L by G as shown. The value of k, which is equal to 2 pi, cannot be found by using dimensional analysis. However, this method cannot be applied to derive equations where addition or subtraction of different terms is involved. For example, we cannot derive the equation S is equal to UT plus half AT square using dimensional analysis, even though we checked its dimensional consistency. Dimensional equations can be used to convert units of a given physical quantity from one system to another, and to thus find the conversion factor. For example, consider the physical quantity force. The dimensional formula of force is mLT power minus 2. The SI system of unit of force is Newton, and its CGS unit is dyne. Hence, 1 Newton is equal to 1 kilogram into 1 meter into 1 second power minus 2. Similarly, 1 dyne is equal to 1 gram into 1 centimeter into 1 second power minus 2. Now, we divide 1 Newton by 1 dyne and then find the ratio of Newton to dyne as shown. Thus, 10 power 5 is the conversion factor to convert Newton to dyne. Dimensions are generally used as a basic test to check the consistency of an equation, where there is a doubt regarding its correctness. However, this test cannot be completely relied upon, especially in the case of dimensionless quantities or functions. Dimensionless constants cannot be obtained by this method. For example, the arguments of some dimensionless functions such as trigonometric, logarithmic, and exponential functions cannot be obtained using dimensional analysis. The ratio of similar quantities results in a pure number, which is again dimensionless. For example, angle is the ratio of arc length to radius, which is length divided by length. Absolute refractive index of a medium is the ratio of the speed of light in a vacuum to that in a given medium, which is the ratio of speed to speed. The test of consistency of dimensions not only tells us the consistency of units, but also helps the user ignore the units to be mentioned and conversions among multiples and submultiples of units. If an equation is put to the consistency test using dimensional analysis, and if the equation fails, it means that the equation is proved incorrect. If the equation passes the consistency test, it does not mean that the equation is correct. Thus, an equation proved to be dimensionally correct need not be an exact equation, but an equation that is proved to be wrong dimensionally must be a wrong equation. The dimensional analysis method is very useful in drawing relationships between various interdependent physical quantities. This analysis can only test dimensional validity, but not the exact relationship between the physical quantities in any given equation. The dimensional method cannot differentiate between physical quantities which have the same dimensions. For example, even though the quantities